So this is section 1.1.3, which covers drift and diffusion currents. And so to begin with, just some terminology. Carriers are basically things that carry charge. So that's your electron and your holes are both charge carriers. And when the carriers move, these carriers generate current. So when the charged particles, such as a hole or a electron, move, then you get a current. So what causes carriers to move? And in the book they present two mechanisms. One is drift, and drift is movement of the carrier particles, holes or electrons, caused by an electric field. So that's one mechanism. And then the other thing that causes carriers to move is diffusion. And diffusion is a movement caused by variations in concentration. So you have a concentration gradient causes diffusion. And diffusion is usually from, high concentration to low concentration. And this concentration gradient can be generated by a non-homogeneous doping distribution. So you have some piece of silicon, and they have areas of high concentration of, say, your N-type doping with phosphorus, versus some areas which have a low concentration of your doping agent. And also another way you can get this concentration gradient is doping of a quantity of electrons or holes into a region. And we'll get back to both of these mechanisms in later parts of the book. And so we won't really talk about more. And so the first thing is, how do we calculate the drift current density? And all these current densities are represented by the symbol J. And so the process is, first we an electric field is applied to the semiconductor. Okay, then the field produces a force that acts on free carriers. In this case, we'll just say electrons and holes. So that's the carriers that we were talking about. And then 3, the free carriers, the electrons and holes, experience net drift velocity and net movement. So we have free carriers, we apply electric field to it, and they move, and they generate the drift current. So in the first part, we're just going to consider an electron, and if we have some electric field, we'll just represent it by E, and this is going to cause an electron to move this direction by the force of the electron is opposite of the movement of the electron is opposite of the applied, and so the electron is going to go this way. And if we calculate the electron drift velocity, and we'll just denote, remember, these drifts are drift velocity density, I should say, is J, and we're going to call this dN because this is a donor electron, and it's going to be equal to minus the mobility, the electron mobility. So this is electron mobility times the applied electric field. And the electron mobility is in centimeters squared over volt seconds. And this is in amps per centimeter squared. And the electron mobility is around 1350 centimeters squared per volt dot second. And it is a measure of how well the electron can move around. Whoops, I did this totally bad. I said I'm talking about velocities, and I write in the electron density. So this is a velocity. Oop. So the velocity of the negative carriers is equal to minus the mobility, and the minus there is because it's in the direction is opposite of the applied electric field. And so now we're going to do the drift current density, which is the J sub dN. Oh, the book just calls it N. And we're talking about the N-type semiconductor with extra electrons around. And so we're going to look at so it's going to be the minus the fundamental charge, fundamental, which is 1.602 times 10 to the minus 19 coulombs, times the concentration of your electrons. And they called it N, which really, if you read the previous lectures, we could call it ND, or depending on the situation, NO, but they just called it N. And so times VD, which VDN, which is what we calculated up here. And then if you put in what that is, minus mu NE, you get plus E in mu sub NE. And so that's the drift current density for an N-type semiconductor. Now we could look at a P-type semiconductor. P-type semiconductor. So that's like silicon that has been doped with boron. So there's lots of free holes around. So we got hole surplus. And there we apply the electric field again. And this time the holes are going to move this way. And we could calculate the drift velocity for the holes. It's going to be mu sub p for the holes times the applied electric field, because now there's no minus sign because they're both flowing in the same direction. And then the mu sub p is around 480 centimeters squared. So this is the whole mobility per volt dot second. So you can see the holes move a lot slower around the silicon than the electrons do. And then we could calculate the whole drift velocity is going to be equal to that minus the fundamental charge. Whoops, no. Sorry. It's going to be equal to the fundamental charge times the number of carriers. Again, from previous ones, we'd call this like Na for the acceptors. And then times VDP. That's not a minus sign there. It should be plus. And that's going to be equal to EP, and then you put in the mu PE, and which is equal to EP mu PE. So that's the drift velocity for the P-type semiconductor. Well, we shouldn't actually call it P-type. We should just call it the semiconductor. Let's get rid of the P-type there. We'll just call it for a semiconductor. Because you could calculate it for, if you had a N-type, you could calculate how many holes are available. Remember, we had, from a previous lecture, we had NO, NP equals NI squared. And if you had a say a P-type semiconductor with the excess of electrons, this would be ND, and then from there you could calculate PO, so equal to Ni squared over ND, or basically your P's. And then you could plug that into there and calculate the drift velocity for the holes. So we could just say drift velocity for holes here. And the other one is the drift velocity for electrons. Electron drift velocity. Whoops, not doing very well here. Drift velocity. Okay. Now the total drift velocity is going to be the electron drift velocity plus the hole drift velocity, which is going to be equal to the E in mu n plus E in EP mu p times the electric field. In the book, they call this whole quantity the conductivity, sigma. And then you could say J is equal to mu times the E. And then also you could say J is equal to 1 over mu, where this is called the resistivity. And conductivity is ohms per centimeter to the minus 1. And this is ohms per centimeter. And so by doping, we can control the conductivity of a semiconductor. So doping controls conductivity. So now I'm going to work an example, and this is example 1.3 in the book. And it basically says, calculate the drift velocity for silicon at temperature equals 300 Kelvin, and it's been doped with arsenic, so that so arsenic is a group 5 element, so that's a donor. Nd equals 8 times 10 to the 15th centimeters cubed. Okay, and so we know that it's given in the problem that the electron mobility is 1350, and the hole mobility is 480, and we know the applied electric field is 100 volts per centimeter. Okay, and so we just covered this, that J is equal to the conductivity times the electric field, which is equal to the charge times the concentration of electrons times the mobility of times the mobility of electrons, plus the charge, fundamental charge, times the concentration of the holes times the mobility of holes, all of that times the electric field. So we know that E is equal to, that's a fundamental charge, 1.602 times 10 to the 19th coulombs. And so the only thing that we're missing is we need to know what N and P are. And so we were given in the problem basically that the number of donors is that. So N is approximately equal to Nd, which is equal to 8 times 10 to the 15th per cubic centimeter. Okay, and then we're given at 300 Kelvin, so we're just going to say P is going to equal to Ni squared. That's the intrinsic concentration over 8 times 10 to the 15th centimeters. And we know previously working this out that this is 1.5 times 10 to the 10th centimeters to the minus 3. So that basically, or that comes out to 28,125 holes per cubic centimeter. Whoops, that wasn't -3. There's no negative on the bottom there. And now we know everything to calculate the drift velocity. We just plug in the fundamental charge, and then we put in the concentration of electrons, 8 times 10 to the 15th, times the electron mobility, which is 1350, and then we put in the concentration of holes, which we just calculated, times its mobility, which is 480, and then all times the applied electric field, which was 100 volts per centimeter. And you come out with J equal to 173 amps per cubic centimeter. So pretty high amps per cubic centimeter. So after this example, they give this little side note. Which has some cautionary advice. They gave out those two formulas, dPn equals minus the mobility of n. This is what we just previously shown. And VdP is equal to mu sub p times E, the whole mobility times the electric field. And the side note basically says, this is not quite true. And for most circumstances true, but it's not quite, because you have each of these have a maximum velocity. You can't just keep increasing the velocity forever. And if you had some chart where you had the applied electric field and this is your V, then eventually it's just going to go to some point and you're going to have what they call a drift velocity saturation. And the book gives a number of 10 to the 7th centimeters per second. So that's the fastest it can go. And then the other thing is that these mobilities of your charge carriers are actually proportional to your doping concentration. And as the concentration goes up, your mobilities generally go down. And that's really what the side note says. Just something to be aware of. Now we move into the diffusion current density. Calculations, and again this is represented by J, which is amps per amps per cubic centimeter. Cubic centimeter is the units for that. And so diffusion is particles, and in our case charge carriers, flowing from high concentration to low concentration. Okay. And so if we start with a electron carrier, then you might have some, and they give some graph, it looks sort of like this, where this is your concentration of electrons, and this is distance x. And then the electrons will want to go to the lower concentration side. So this is your electron flow, but current is given the opposite direction. So this is the electron diffusion density flow direction. And we calculate this electron diffusion density is equal to the fundamental charge again times the electron diffusion coefficient. Electron diffusion coefficient times the concentration gradient of the electrons, dN dx. And likewise, you could have a similar graph for your holes now, concentration of holes, where this was electrons. And again, x and distance, and a little graph showing increased concentration. And now your holes want to go this way, but also your hole diffusion current density, I think it's called current density. Yeah, current density is going that way also. Because current is the flow of positive charge, and then we could calculate the current density for the holes is minus the fundamental charge, and the minus sign is there because of the holes have a different charge than the electron, times the diffusion coefficient of the holes times the whole concentration gradient. And so those are the two equations for holes. And now we're going to work another example. And so this is example 1.4 in the book, where they're asking calculate the diffusion current density for silicon at T equals 300 Kelvin. And we're given that dN, that's the diffusion coefficient for electrons, is 35 square centimeters per second. Where's that cubic? Let me look that up. And then we're given that dN is equal to dN dx is equal to 10 to the 16th, or basically the number of electrons is 10 to the 16th at 3 centimeters away, and 10 to the 12th at 0 centimeters away. And that's given in the problem. Actually, it's micrometers, actually. 10 to the 6 times 10 to the minus 6 times, there's 100 centimeters in 1 meter. And so you just plug that all into your drift equation, and so you have 1.602 times 10 to the minus 19th coulombs times your dN. So this was E. This was your dN, and then this is here. That's your dN dx. And if you plug that into your calculator, you get 187 amps per centimeter squared. And we're ignoring JP because we're assuming, because of the doping, that this is much, much less than JN. And so we're not even going to bother to calculate what Jp is. Because your total current density is going to be, I'll call it T total is going to be Jp plus Jn. But we're assuming that this is just so small it's pointless to calculate. And then the author shows this sort of neat little relationship called the Einstein relationship. Where it shows that the drift and the diffusion are not totally unrelated. And so if we had the diffusion of an electron over the mobility of an electron, it's equal to the diffusion of a hole over the mobility of holes, which is equal to kT, that's a Boltzmann constant, times the temperature, over the fundamental charge, and this all comes out to be 0.026 volts. At room temperature. Okay. And if you look at these two examples that we've done for diffusion and drift, you know, we're getting around 200, approximately 200 volts per cubic centimeter. And so if you had this, say, some device or semiconductor piece and you wanted to have 1 milliamp going through it, your total current is going to be your diffusion current times your cross-sectional area. So if we had say 1 milliamp, and we have a current, say a drift current, because one of these is going to be the dominant factor in your semiconductor, either the drift or the diffusion. And then we could calculate A is equal to your cross-sectional area is going to be 5 times 10 to the minus 6 cubic centimeters. So a very tiny thing. And then if we just kind of converted this to micrometers, so 5 times 10 to the minus 16th cubic centimeters, and then we'll just do a little dimensional analysis. 100 centimeters in a meter, and then there's 1,000,000 micrometers in 1 meter. And then if we plug that all in, we should get 500 micrometers squared. So that's the cross-sectional area. And so if we represented this by a little circle, that would be the cross-sectional area here. And the area for a circle is pi r squared. So if we put in 500 square micrometers times pi times r squared, then r is going to be equal to 12.6 micrometers. So the radius is very tiny, 12.6 micrometers, very tiny. So we're talking about very small devices that semiconductors are. Then the last thing for this section is I'm just going to do a piece of another example. So this is example 1.4, where they want you to calculate the diffusion density for the holes, and you're given this is silicon at 300 Kelvin, and the hole concentration as a function of position, it's given as 10 to the 16th times e to the minus x over LP, where LP is equal to 10 to the minus 3. Okay? And you're also given that the dP, that's the diffusion coefficient for holes, is equal to 10 centimeters squared over per second. Okay? So you're given that information, and then all you have to do is plug it in to your formula that Jp is equal to minus E times the diffusion of the holes times the concentration gradient. And so we get minus times 1.602 times 10 to the minus 19 coulombs. And we have the 10 there. And then we have to evaluate that differential, which is going to be 10 to the minus 16th times minus 1 over LP, which is 10 to the minus 3 times E. And part A is they wanted at basically x equals 0. And then you're going to have e to the 0. And this is going to come out to be 16 amps per centimeter squared. And in part B, I'm not going to do it. They just have x at some other distance. And you just basically apply the same formula again, but put in the x at a different distance. So that concludes this next section.